C'è questo.
Have you read the report?
No, schermo finestra dell'applicazione.
Matteo, have you read the report?
Vedi,
So you'll learn
questo lavoro.
something at least about what's in the report.
Che sembra che
This is what
ci
the
sta
talk is
condividendo lo
about.
schermo, quindi a questo punto.
No, it just came out. It's new. It's brand new. So that's the point.
So it was not to read before.
No. I'm telling you about this report. The purpose of this talk is to publicize the report.
Io vado a controllare che effettivamente.
Yeah.
This is for the bibliothèque. For the library.
It's Tommaso's copy. But everyone, you didn't go to IAPC. Everyone at IAPC got a copy. It's true. It's a good idea. I could leave a copy with I don't have a copy with me, but you can get a digital copy.
Okay, can you make a self-introduction?
Yeah, in fact, this is, I'll introduce the talk and at the same time say who I am.
Because I think that
This thing's on wheels.
Ok, we are online.
Okay. So, Tommaso, just tell me when to start. Okay. Okay. Hi, everyone. It's a little loud, but I thank you for coming and inviting me to give this talk. What I'll be doing is a brief briefing on the National Academy's report that just came out this year called Volcanic Eruptions and Their Repose, Unrest, Precursors, and Timing. That acronym is thanks to Michael Manga, who came up with that clever term. And I am the fourth person on this list here. I'm Amanda Clark, and I'm an associate professor in the Arizona State University School of Earth and Space Exploration. I'm also an associated researcher here at INGV, and I have been associated with INGV PISA for almost 8 years now, I think. But I've been collaborating with many people at INGV for even longer. This is the authors of this report, and I will be summarizing it because that's part of our mission as the committee to disseminate the information that ended up in this report. So I want to start by giving a bit of information about how the report came about and how it was commissioned. And so many of you in Italy may not know about how this process works, and I didn't know until I participated. So the National Academies of Science, Engineering, and Medicine were founded in 1863 during the US Civil War by an act of Congress signed off on by Abraham Lincoln. And their purpose is to provide independent, objective advice to the nation and the government on matters related to science and technology. And part of that independence is maintained because the Academy receives no compensation from the government for its services. So it stands as this independent entity, and its headquarters are here in Washington, but they have many facilities around the country. They're right across the street from the State Department, if you're interested. So the main thing that you may know the academies for are their fellows or their members. So there are just over 2,000 lifetime members who have been elected via a very strict process, 450 foreign associates. Many of this group are Nobel laureates, and it's a fairly lofty group, and it's a rather high honor to be elected to the Academy. The Academy, however, also has a lot of permanent staff members, and they make use of experts and scientists and people from around the US to generate the reports that are put on their mission. So even people like myself, who are not a member of the Academy, can participate in this process and write these reports. So they try to draw on a broad range of people throughout the country on an ad hoc basis. So the basic process is that typically it's a federal or state government agency that defines the study. And so what they do is they get together with staff members from the national academies, and they define the tasks for their study, and they define a budget. Once that set of tasks and the budget is defined, they have absolutely no input or control over the content of the report that comes later. And at the end of this presentation, I can show you the website where you can download reports and also surf around and see the variety of reports that have been put out over the years. So then there's also a process of committee selection. So there's nomination, the committee is selected and approved. They're specifically sought for their range of expertise, their breadth, as well as their screen for conflicts of interest. So no one on the committee can have any financial or personal reason for caring about the specific outcomes of the report. And then the report process is basically, as you might imagine, which is committee meetings, and many of those committee meetings are required to be open to the public, and they have to be advertised in advance, so sort of your average person off the street can enter these meetings, watch and ask questions. And so that's one kind of key part of it, so that it's kind of this open, transparent process. The other thing is that we were 12 on the committee, but of course we sought information from people outside of that committee because they have expertise. And so one of the things that we did in this particular process was have a workshop in Washington, D.C. in August of 2016. And we invited a range of experts from around the world and around the US to give talks on specific things, which was, the point was to summarize the state of the art and then give their vision for what they thought the future was. And we compiled all that information as part of our own process. So for example, Augusto Neri and Mike Burton were two people that were invited to that process. Also, Guido Giordano was the person who launched it and provided a vision at the beginning of that workshop. So they were quite, Italy was quite well represented. And then the main part of the writing and the decision-making occurs in private amongst the committee in order to maintain that level of independence. Then there was a process of, I think we had 15 reviews for this report that were, again, people that didn't have a conflict of interest. And they made very lengthy comments on the report, and we had to address every single one line by line. And so that's part of the Academy's process. And then members of the Academy reviewed our responses to those comments. Okay, so this particular report came about as a commissioned report from the National Science Foundation, who funds most basic research in the US, including earth sciences. NASA, who funds a lot of earth sciences, as well as earth observing satellites and instruments. The US Geological Survey, who is the home of the Volcano Hazards Program and the Volcano Disaster Assistance Program. So our tasks, so when I entered this committee, the tasks were already defined, and they were to start by summarizing the current state of understanding of how magma is stored, ascends, and erupts, discuss new research that could improve forecasts of the type, size, and timing of eruptions, observations or instrument deployment specifically that could improve volcanic quantification of volcanic processes and precursors, and then identify priority research and observations needed to improve fundamental understanding of volcanic processes, with the eye towards those fundamental understanding going towards better monitoring and forecasting. So this is just a picture of Pavlov volcano, an eruption in 2016 that we used to sort of explain the range of interests that we had in this project. So we were interested in all kinds of volcanic processes, including things like drifting ash clouds, lahars, the possibility of caldera eruptions, as well as different kinds of data that would go into this process, which include things like ground-based measurements that already exist or future measurements, and space-based instruments. So one of these reports, I didn't explain this initially, but one of the things about these reports is they are meant to be consumed by anyone and everyone. So they should be technical enough for an audience like you to appreciate them and sort of respond to them. But at the same time, program directors at National Science Foundation and NASA should be able to consume them. And more importantly, they should be able to take that information and pass it to someone like a senator or a member of Congress who is making decisions about funding of science in the future through those programs. So there has to be sort of this general motivation for people who don't ordinarily care about volcanoes. So we had to write this beginning chapter, which was a much more general chapter. So one of the things that we kind of highlighted is the fact that the US has 169 potentially active volcanoes. 50 have erupted in the last 30 plus years. In this image, you can see the red volcanoes have erupted since the year 1800. Yellow have erupted in the last 2,000 years, and the black have erupted before that, but are potentially active. And then an alarming thing that we found out in this process is that fewer than half of those have a seismometer, and only 3 have continuous gas measurements. So we're really kind of lacking in instrument infrastructure in the US. And just to sort of point out here, approximately here is the border with Mexico, and this is the Canadian border through here, and then Alaska begins again through here. So we've included neighboring volcanoes just because they will have impact on the US if there's an eruption. The other thing that we tried to do in the intro section was to compare volcanic eruptions to other kinds of hazards that people may be familiar with. And this is probably something that people at INGV are also familiar with because you work in a multi-hazards environment as well. But for example, we set up this, we kind of modified this plot of precursor times where you have long precursor times out here to the left, as well as the event duration, so that you have the event duration increasing in this direction. So we put things on here that people would be familiar with. For example, Hurricane Sandy and Katrina. We have hurricanes in the US every year, and typically it's fairly predictable in the sense that we almost always have days of warning. And then as those days progress, the models that predict the specific location of landfall converge to something that everyone agrees on. And so within hours, notion of what this thing is going to do. And then all total duration more than some days, depending on the overall outcomes. Floods can be a long duration. On the other hand, something like earthquakes, as you all know in Italy, you have virtually no precursory activity or no precursors that tell you exactly when something's going to happen. And those lasting seconds or minutes, but then aftershock swarms or search and rescue lasting long duration. But if you look at this image, you can see that volcanoes, and this is a good point to convey to the general public, is that this kind of volcanoes span this full diagram. So you have something like Kilauea in 1983, which had weeks to months of precursory activity, and then has had decades of ongoing activity. This is kind of just this extended event. You also have something maybe a little bit more standard or a little bit easier to manage, such as St. Helens type eruptions, where you have weeks to months of precursory activity. Then once the event starts, you have the main activity concentrated in weeks to months, but then that may extend into a few years. But then there's this complex issue of someplace like a resurgent caldera, like Long Valley caldera, and I think some of you have been concerned about this with in terms of Campo Flegrei. So in terms of Long Valley, has been decades of precursory type activity, but up until now, no eruption has occurred. And so this is kind of one of these ranges of possibilities that is special to volcanoes. The other thing I want to mention is that it's worth noting, especially when talking to generalists, is that volcanic eruptions, aside from impactors, are the only events that can have global effect as well as can create extinction level events. And so that's something that on the sort of the scale of things, volcanic eruptions have this potential that far exceeds most natural disasters that occur more frequently. One of the first things that we did was to define some grand challenges, and then these kinds of themes will continue as I talk about this report. And so I'm just going to summarize what we found in the report, and then hopefully we'll have some questions at the end. So the grand challenges were first, and it sort of comes from our task, were to forecast the onset, size, duration, and hazard of eruptions, and in particular by integrating observations and quantitative models of megadynamics. Another thing that kind of was a recurring challenge or recurring point of discussion was the idea that we need to quantify the life cycles and volcanoes globally to overcome our current biased understanding. This is a term we used a lot, is that we have spatial, temporal, and scale bias in what we know in volcanology. So generally speaking, we have, sort of not a very long history in our science. And especially when it comes to monitoring and prediction, we have, most of our knowledge is based on very, very well-studied volcanoes that aren't very numerous. And so, and most of the well-studied and well-monitored volcanoes have been in the developed world, whereas volcanoes in the developing world are lacking that kind of monitoring and that kind of intense study in general. And then, as you all know, we've not seen or witnessed or recorded eruptions that are on this grand scale of caldera-forming eruptions. So that's where we are sort of limited in our viewpoint, is quite small in terms of time and scale, when the actual behavior of the volcanic system is much broader. And then the other thing is that what we found in the US, and this will come up in one of the chapters, is that we needed a coordinated volcano science community in the US in order to maximize scientific returns from any eruption. Okay, so I will start with forecasting eruptions and what that chapter decided were sort of the key questions and the key issues. And please stop me if anything is not clear or if you have questions. So, forecasting eruptions, the forecast is a probabilistic assessment of the likelihood and time of volcanic activity, and that forecast may also include the style, duration, and the consequences. Historically, as you may know, is that most forecasting is either based on the geologic record or monitoring data via a semi-quantitative or semi-qualitative pattern recognition, or some combination of those two things. And there have been some notable successes in this regard, but very few eruptions have been forecast, especially in levels of detail related to the style, duration, and the consequences. And so one of the things that we wanted to look at and sort of make it clear to the people reading this report is that we should be trying to follow along perhaps in the weather forecasting community, where you have physics-based models combined with space and ground-based data, particularly in real time, in order to make better forecasts. Let's see. There we go. Okay, so some of the key questions that came out of the forecasting part were, this is kind of an interesting thing because this came up at the Long Valley. What physical parameters and processes can be used to better forecast whether an episode of unrest will culminate in an eruption? And as we know, caldera-forming eruptions tend to be quite restless. And so these tend to be the kinds of grand scale possibilities that tend to have these long periods of unrest. And so we thought that was a priority in forecasting. How can precursory phenomena be used to forecast eruption intensity and style? And one of the other key science questions was, what was the best way to estimate the depth and volume of eruptible magma and use it to anticipate the magnitude of an impending eruption? So one of the things that we talked a lot about were the fact that there's a whole lot of magma that doesn't get erupted. And this is represented in the plutonic record. We don't have a complete Pluton record, but there is some notion that that there's a whole lot of magma that doesn't get erupted, and sort of understanding when an eruption doesn't happen versus when it does happen, and then what proportions of that magma ultimately reaches the surface is a question that is still, I think, fairly poorly constrained. And then another problem that sort of some of the observatory people brought out in the workshop is that once an eruption begins, especially these long-lived things, it's very difficult to understand when it will end and whether it has ended. And I had this experience also when I worked as a student at Montserrat Volcano Observatory. So when you have a long-lived eruption, but you have these periods of quiescence, and then it's unclear whether that constitutes the end of the eruption or not. Okay, so the research priorities that go along with those kinds of questions are to, and this is kind of an obvious one, and it's kind of give us everything everywhere, which is implement multidisciplinary monitoring and geophysical imaging for as many volcanoes as we possibly can. And this is sort of geared towards overcoming the bias in the record and unifying our understanding of volcanoes in a broader sense. Another thing that was put in this report is that we wanted to develop flexible open access databases for diverse observations and have those for immediate use. And so this could be controversial in that we have a lot of databases in the US. Those databases are incomplete. A lot of kinds of data, a lot of types of data are not data-based. And most of it is not data-based in real time or for immediate use. And so this was something that we put in the report as something that would benefit overall understanding. This may be controversial amongst the USGS folks, for example. The other thing was that we had a minimum goal of putting one seismometer at least at every possibly active volcano in the US. It turns out we have a lot of seismometers in the US, but not one at every volcano, as we said. There's only half of them are covered. And then to capitalize a little bit further on daily monitoring from satellite instrumentation in a more automated way. There's some notion that we don't use the NASA resources in the same way that, in the way that we could be. And then we also wanted to develop, sort of key part of this process is develop and test physics-based forecasting models that assimilate monitoring data in syneruptive observations. The only thing I wanted to say here is that this is in blue because for each of these chapters, I've put in blue the research priorities that occur in multiple chapters. And so when we did this report, everybody worked on all the sections, but some groups were sort of really in charge of chapter 2, and some were in charge of chapter 3 and chapter 4. And so it turns out independently, we came up with a lot of things that overlap in terms of research priorities. I've highlighted those in blue, that these are the things that came up repeatedly from separate discussions. Okay, so one of the key things that is sort of the biggest paradigm shift that comes out of that forecasting chapter is that there should be a big push, and many of the people at the IMGB are already doing this, but there should be a big push to generally move the community from pattern recognition or semi-quantitative pattern recognition of monitoring data to model-based forecasting that is linked with that data. And a big chunk of that's going to include establishing a link between volcano plumbing models and next generation monitoring data, or any monitoring data. And then being able to use those physics-based models in real time, analogous perhaps to the weather forecasting models that assimilate data on an hourly or half-day basis. And then a key part of this is a caveat and a sort of a charge to the community is to make sure that model intercomparison and validation are happening continuously and all the time. So that's sort of the big mandate of this report was to sort of gear everything towards prediction and monitoring, because that's what we were told to do. But as part of that, in order to make any of this happen, better fundamental understanding of volcano dynamics is needed. And so then we have this other chapter which breaks down the system to subsurface, eruption, or sort of almost eruption, into eruption characteristics. and then we highlight some of the fundamental things that need to be addressed in those fields. Okay, so this is how we broke this down, was to how magmas are stored and transported in the crust, so that's the subsurface, how do eruptions begin, evolve, and end, and that's kind of near surface, and then what happens when volcanoes erupt, so sort of how do you predict the path of a lava flow, for example. Okay, so in this talk, I just give a few examples of the figures that we use to highlight what we do know in sort of a general sense. And then that leads us to sort of being able to state what we don't know. So in this figure, we took this as an example from De Gruyter and Huber. They plotted here, let's see if I can get a mouse, yes. So on the horizontal axis, you basically have rapid injection into a storage zone from depth. So that's kind of rapid recharge. And on the left, you have rapid crystallization, which means you're not getting much recharge, you're mostly having a cooling magma body. On the vertical axis, we have viscous, kind of squishy, easily deformed crust. And then on the top of this axis, it's kind of stiffer, elastic crust that's not so easily deformed. And so you can sort of break down sort of behaviors of a magma chamber and whether they lead to an eruption or not in this way. And so, for example, you can have in this upper right corner in sort of stiff crust with rapid recharge, you can have eruptions triggered by mass injection. Or if you have a little bit more flexible crust, you can have bubbles forming in that zone with injection from the base and due to heating and more gas coming into the system, and those eruptions may be triggered by buoyancy. On the bottom left, you have something where you have a viscous, flexible crust and sort of not very much recharge and cooling, and that's kind of where you don't have an eruption, where nothing happens, and that's kind of represented by the Pluton record. So these are your Plutons, and you know, that's the magma we don't know about because it's stuck down there. However, this is a simplified picture, but we use this to sort of frame what we were looking at, and then sort of take it to sort of more detailed levels, including putting numbers on some of these detailed processes that we're talking about here. So from the point of view of sort of this magma storage zone and sort of what happens to magmas in the crust and the subsurface, the key questions that we asked were, what causes ascending magma to stall at different levels in the crust? We know a lot about this, but we don't know a lot of details. How are erupted bodies of magma assembled and what is their lifespan? You know, there's a debate about, are they assembled in one grand squish from below and then periodically recharged, or are they built piecemeal over long periods of time? The other question that people have asked is, how quickly do magma bodies mobilize before erupting? And this is a big question at some place like Yellowstone. If you've got Yellowstone or Campo Fleury sitting in your backyard, how much time do you have before an injection from depth that may be detected by seismic signals? How much time do you have before that body is mobilized for eruption? Is it a fast process or a slow process? And I think we don't know. I think people have different ideas. And then again, back to that question of which portion of that magma body, let's say you image it, but what portion of it actually is eruptible material? So the research priorities that go along with that, now remember this is, the blue is things that appear elsewhere and in other chapters. So one of the things that we thought we don't do enough of is detect the location of magma by using petrologic analysis or geophysical visualization techniques or imaging techniques. And that we should also continue to use the petrology to look at the timing of magma residence and ascent. And as we get more and more technical expertise in these areas, this is not my field, but petrologists, they can put finer points on that timing. Better constrain the properties of magma, density, compressibility, rheology. This comes up again and again. It turns out we don't really know that much about magma properties, especially over a wide range of conditions. This comes up multiple times. Build models that couple large-scale transport with fine-scale processes. And this is something that INGB Pisa has been leading in for quite a long time. And then this I thought was kind of an interesting point here, was to integrate the volcanic record and the plutonic record to sort of extend that lifespan and extend from what does erupt into what doesn't erupt, and sort of link that whole time scale slash magma supply scale together. Okay, so that's where we ended up with that chapter. So how do eruptions begin, evolve, and end? This is another thing. So again, we know something about eruptions and why they behave in the way they do, especially in a general sense. So this is sort of basic level information where we've got viscosity here on the x-axis and discharge rate on the vertical axis. So for low discharge rates and low viscosity magmas, we expect things like strombolian and effusive kinds of eruptions. As you increase that discharge rate, you get into sort of high fountaining Hawaiian eruptions. And then as you move into more viscous systems, you end up with sort of on the low discharge rate and effusive domes and coulees, and then this sort of these large scale eruptions. However, a lot of this kind of overall structure of how we think about volcanoes and the way they erupt ignores a lot of complexity, in particular unsteadiness, conduit evolution, and I mean geometric evolution of conduits, and interaction with external water. And this is something that often gets left out of these overall maps. So one of the things that we listed here was that how can initiation of an eruption be predicted from geophysical and geochemical precursors? This is kind of the holy grail of things, right? This is a basic level question, and it's not that easy to answer. This is something that I've been interested in my own research for quite a long time, is what are the critical thresholds that govern shifts in eruption style? So going from effusive eruptions to explosive eruptions, or vice versa. How do conduit and reservoir geometries evolve over time? And why do volcanoes stop erupting, and how do we recognize when an eruption is over? Again, that's a question that came up before. The key research priorities, and all of these I think overlap with other parts of this document, are to perform field and experimental measurements to constrain magma properties and to quantify time-varying and disequilibrium processes. So, like I said, and as many of you know, a lot of our general under steady flow rates or steady continuous constant values. Many of the models that we use to understand systems are assuming an equilibrium process. Another thing that came up was to elucidate interactions between magma and external water. This is sort of a key thing because that can precipitate eruptions or be the onset of eruptions. And again, develop dynamic time-varying models that couple large scale with small scale. So this is kind of the priorities that we think are kind of most important for answering the kinds of questions on the previous slide. Okay, so this is the last kind of big chapter in this report, and this is kind of what happens when volcanoes erupt. And so I will try to, I have a few more slides, so we don't have too much more time to go. So we do know a lot about kind of what happens when volcanoes erupt. For example, in effusive eruptions, we can plot this kind of system on mass discharge rate and viscosity, where we know that as we increase the mass discharge rate for low viscosity magmas, we move from something like Pahoehoe to Aa, and then perhaps into things like lower igneous province or sheet flows. And then if you increase the viscosity, you typically end up with dome or spines, and then as you increase that discharge rate, you end up in explosive eruption. But for effusive eruptions, there are a lot of things that we don't know about the magma properties, especially as the eruptions evolve. In particular, for lava flows and lava domes, they're spanning wide ranges of yield strengths and viscosities. And these are the kinds of things that are very important to the overall transport of these things. And so there's a lot of fundamental stuff that we don't really understand. Okay, and then we can there are a number of figures that we used for explaining explosive eruptions, but this is one that we included from Augusto Neri and Dobran from 1994, where you can sort of use this, we modified this, and we can use it as a proxy. As you increase exit velocity along the x-axis or increase the vent diameter along the vertical axis, you can start to map out behavior of explosive eruptions in a way that is useful. For example, you have collapsing columns at the left, and you have rising plumes at the bottom right, but there's a whole swath of behaviors in the center that are oscillating or mixed types of eruptions. And a lot of the sort of assumptions that go into modeling this and mapping out this regime diagram make some assumptions, such as steady flow at the vent, possibly limit the number of particle sizes, as well as some of the information is not cemented in terms of the actual values that control which regimes we would be in. So if we think about effusive eruptions or explosive eruptions that already have started, some key questions that we highlighted were how do time-varying mass flux and magma properties affect eruptions? So this is this kind of thing where stuff is, so the vent flux is not necessarily steady, and the viscosity and material properties change rapidly over time and space. How do particle scale processes influence the large scale dynamics of eruptions? This is something that people at INGV PISA have been working on also for a long time, but it's still evolving. What is the role of an evolving substrate in controlling flow dynamics? So that could be when you have a changing topography under a lava flow, or when you have pyroclastic flows that erode their own channels or change the shape of the channels that they're passing through, or lahars who fill channels perhaps, or erode channels. What are the key processes driving dispersal in magma-water interactions? And then what processes govern the occurrence of and dynamics of submarine explosive eruptions? And these two are in red only because originally put them both together in sort of water magma interactions, but we thought that these two things deserve their own separate emphasis, so that explosive eruptions, phreatomagmatic eruptions, were important on their own, and then the submarine eruptions I think are important largely because we know almost nothing about them. There's a very limited knowledge base in effusive and explosive eruptions under the seas. And so we separated them to emphasize them. And then sort of interactions, we emphasize interactions between volcanic plumes and the atmosphere. I will just say one little brief thing here. I left a chapter out of this briefing, which is related to how do volcanoes interact with the atmosphere and energy. I didn't have time, but there's a whole chapter in the report on interactions between them. Okay, so the research priorities that go with this are develop techniques to measure temporal variations in eruption rate, and this means in the field or potentially in the laboratory. Integrate models of small-scale processes and large-scale dynamics. Again and again, this came up independently with the different discussion groups. Undertake model verification, validation, and comparison in a variety of ways, which includes getting data during eruptions in real time, whether that's sample collection or looking at seismic data or gas data, and integrating those things in real time. And then overall, we wanted to overcome our biased understanding by looking at the kinds of eruptions that we don't know much about. Those include really, really big eruptions, caldera-forming eruptions, and submergence. And so that sort of modified these a little bit, but there I compressed some of these notions. So to go through the common themes, there were basically 3 common themes, or we sort of summarized the things that just kept occurring over and over again in this report, which were to develop multi-scale. You combine volcano scale dynamics with bubble and crystal scale processes. This is something that I think and is an important part of all different forecasting to subsurface to subaerial kinds of behavior. High resolution measurements at more volcanoes and throughout their life cycle. And when I say high resolution, that means high temporal resolution and potentially high spatial resolution. And this, again, is sort of to go towards overcoming our observational biases and to address this issue of unsteadiness, where we can get into rapidly time-varying magma properties or eruption rates. And then synthesize during the forecasting process and during the scientific study process a broad range of observations from subsurface to space. Okay, so this is kind of the grand idea, and it's easy to say but hard to actually do. Okay, so then I just want to finish up with a couple of comments. We added this chapter, even though it wasn't part of our mandate specifically, but basically what we just said was that in order for any of the things such as forecasting or fundamental science improvement to happen, we need to have support for building a science community, a volcano science community. And so support for interdisciplinary collaboration and training, which Europe does quite well. The US does not necessarily fund, and we're far away from each other, and we don't have funding pools to come together, cross-train, or be seconded, have students seconded to other people. So it's difficult for us as volcanologists in the US to work with one another because, they're 3,000 miles away or something like that. And there's no funding to support the visits. We're trying to rectify that now. Databases, like I said before, databases are reasonable in the US with the US data system, but there is a need for growth into different kinds of data and perhaps less of a moratorium on the data. Shared community infrastructure, we have shared community infrastructure, and that should be expanded. It's particularly associated with petrology or ways to analyze rocks, and in terms of seismic deployments, but there isn't a lot there for active volcanic systems. New technology and instrument development, which can be high risk but high reward, and there's very little funding for that kind of thing in the US as it stands. And then another thing that is kind of lacking in the US is a good relationship between the US Geological Survey, who runs all the observatories, and academic scientists. And so there are collaborations, but they're ad hoc, and they shouldn't be ad hoc. They should be more formalized, and they should be encouraged. And so there's this natural disconnect between the two, and that's something that maybe some of this interdisciplinary collaboration and training could help. So those two things could go together. And then all of that should lead to some kind of preparation for a coordinated response by the scientific community for the next big eruption in order to maximize returns from that are scientific and not strictly in terms of hazards and that sort of thing. So we obviously recognize that hazards and monitoring are important, but there should be scientific goals as well established in advance, so that when a crisis occurs, there can be smart collection of useful data for the long-term development. So that's the idea. Okay, and so then I just want to thank you for your attention, and then this is the website where you can get all the National Academy reports, and you can download this report. Do you mind if I hold it up? Everyone got at IAPSI. You can download or order a hard copy for pay. So you can just go to the National Academies, and you can just type volcano search and some things will come up. There's been more than one, but none. So for example, there have been some on specific volcanoes. Some of them are older than others. And then here's this report, which is a consensus study report. So anyway, that's all I had to say. And it was kind of part of my job of kind of writing that report to also get that information out to the community, and eventually, hopefully, that will generate discussion. Thank you. If anybody has any questions, they can ask. I know it's a lot of information, but I wanted to push it out there and let you guys think about it. And also, please take a look at the report.
In one of your first slides, there was a
Oh yeah.
In one of your first slides, there was a reference to the fact that an eruption forecast is a probabilistic assessment of something.
Yeah, let me see. This is from the other chapter. Let's see. This one. Oops.
One of the first slides.
No, sorry.
Okay, that's not important to get there. Just to say that apart from that,
Yep.
doesn't seem there is much attention to uncertainties and probabilities in whatever it shows. I haven't read the report, and I don't know what its content is. But the overall impression, and I don't know if that is the position of the academy, but the overall impression is that if we reduce the epistemic uncertainty, or if we increase knowledge of the facts around volcanoes, we can forecast volcanic activities. Epistemic uncertainty is only one part of the uncertainty. There is also aleatoric uncertainty. Aleatoric uncertainty is that uncertainty coming from the fact that volcanic processes are governed by highly nonlinear dynamics, and they are governed by exceedingly large number of degrees of freedom. So that part of the problem suggests instead that even if we increase knowledge or reduce epistemic uncertainty, we may now be able to predict volcanic eruptions. And I didn't see that sufficiently represented in this report.
Yeah, there is quite a lot about uncertainty. It's not in this briefing, but it is in the report. And a lot of that is also, I'm trying to remember how it ended up. We had multiple versions of that chapter, but a lot of it was also incorporated into this probabilistic assessment, right? So that it's not a deterministic assessment or prediction, it's probabilistic. And in part of that probabilistic forecasting, there is the uncertainty of possible outcomes. If that's what you mean, yes, of course, increasing understanding will decrease our uncertainty about certain kinds of processes. But there's a lot of uncertainty that should get enveloped into the probabilistic assessment. And I believe there is a whole section about that in the chapter 3 on forecasting. Did you want to say something else?
No, I just wanted to say that a report like this one, which comes from academic science, and which therefore gives the society the state of the art of our understanding and where we are and what we believe our science is and where we should go next. It's something which is really relevant because it directly impacts the society. It gives the state of the art where we are, what the highest scientists know, where we should move forward. And this kind of reports are the places where exactly what are our limits in understanding, or our understanding of the limits of our science should be very clearly reported. And that's maybe the case with the report. I haven't read it, and maybe it's a report of interactive states. Even when summarizing things in a presentation like this one, I think either there is a relevant role to the fact that we know that decreasing epistemic uncertainties is not solving the problem. It's not giving us the capability to predict volcanic eruptions. Either we make that point very clear, or we don't believe that's true. So that shouldn't be, I mean, somehow given for granted. It must be communicated, or it must be said that we think that electronic uncertainties are really important. Either we can reduce the systemic uncertainties and know the problems, or electronic uncertainties are relevant, and we have to live with a world where uncertainties will be still there. And we should communicate that in this kind of report.
Yeah, I think that's where this probabilistic assessment comes from. I mean, I'm sure it's like this in Italy, and it's like this in the US. People are very used to getting weather reports with a certain percentage, quantitative percentage and probability associated with that. And people can handle that. They can process that, and they accumulate that sort of, whether they're willing to take that risk of not carrying an umbrella, for example, or whether they are willing to take that. And so I think that's the framework that we want to be fitting into, which is, it's the same with hurricanes, for example. So we know that the hurricane is there because you can see it. You can take measurements, but you don't know the path of the hurricane. People model the path of the hurricane. There are multiple models for the hurricane, so we don't know where it will make landfall until perhaps at the last moment, because that can change. So people are willing to accumulate and take that probabilistic assessment as something that is quantitative, but encapsulates some of that uncertainty inside of it, inside of the assessment. And so I think that's the aim, and I think that with volcanic eruptions, I think it's reasonable to think we can put people in that same framework. Of course, it's not 100% certain, but we can assign what we think is going to happen with some level of probability associated with that. I think that, and not only would we like to do that with the sort of the likelihood as part of that probability, but in terms of within a certain amount of time and at what scale. So our discussions definitely included uncertainty, and that's kind of the overall framework, and I think that's a reasonable thing to expect out of the community in the long term. Yes. Sorry.
So in one of the slides, I think one about forecasting, if you can.
This one?
Oh, no.
Okay, sorry.
Where the no, maybe. So there was some suggestion that there should be a shift from
Yeah, this one.
pattern recognition to use more.
Yeah, this guy.
Yes, moving from pattern recognition to model-based forecasting is a paradigm shift. So I'm thinking about what is done in other fields, like there is sometimes a shift in the other direction using big data, artificial intelligence, neural networks, where they just collect a huge amount of data and they use something to interpret the data without trying to understand the physics of the processes. This is something that you have discussed in your meetings or in the reports.
Yeah.
Like in medicine, for example, there is the use of IBM Watson, so a large supercomputer that just analyzes the data to try to do some results without a real understanding of the process.
Yeah. I guess there are two things. Definitely we had this discussion. And so sort of, and some of that comes out a little bit in this report, which is the more data you have, the more volcanoes you have, the more you're going to understand, or the more you might sort of recognize kinds of behaviors. There probably was a bias in the group, in the sense that we were all volcanologists. There weren't people who were big data people. We were volcano people, geologists and physicists. And so I think there probably, within the group, was a natural bias towards overall understanding. Although that was one of our tasks, was to give state of the art of what we understand already, and then talk about what better understanding do we need to have of volcanic systems in order to make better forecasts. So I think, there was a bias in the questioning as well as in the group. Having said that, this pattern recognition and big data thing, I'm not sure it exists for volcanology. This is the problem. There are some specific volcanoes that have a ton of data, and some of them are here in Italy. So there might be enough data in some volcanoes, from some volcanoes and some eruption periods in Italy to kind of crunch the numbers. But very few volcanoes have that kind of luxury of having this huge amount of data that actually could be processed in this way. Not to mention, as the whole bias suggests, the science of volcanology is young. We've observed a narrow range of eruption styles, and very few volcanoes that do erupt are collecting enough data. And it's sort of spatially, temporally, and scale-based bias. So I think that could go in the next report in 20 years or 10 years. If we actually do some of the things, which is to collect a lot more data and a lot more volcanoes, we may have enough data to sort of think about taking that as an alternative. I think there were things going on, which is, I don't know what you guys think, but I just don't think volcanology has the kinds of data that other fields have in that way, that encompasses the wide range of activities. And our committee might have been biased because it was a geologist, physicist, and volcanologist, to be honest, yeah.
Other questions?
So if someone's saying I can comment a bit more on this, because that's true, and actually having large data available for volcanological studies is really absolutely fluent. And there are recommendations coming along the way from a number of sources. One has been also the last ERUPT motion, where one of the outcomes is that we definitely need organized data for volcanic activities. There are some databases today. One is the global volcanic
Yeah, sure, yeah, absolutely.
Yeah, another one is the LAMEFE, which is organized by Bristol and VGS.
Yeah.
Yeah, another one is very recent, comes from Iceland, and there is an increasing activity on the need of creating databases of volcanic activity. So Wolf has done a lot of force in that direction. Database of unrest, and that's really absolutely relevant. I'm absolutely convinced, and I think everyone is absolutely convinced that we need more data and organized data. And again, I think that this is something that should very well be part of the recommendations by committees. I don't know if there is room for recommendations in reports like
It's not allowed.
Okay.
We said what we thought, and that's it.
Okay.
Yeah.
But there are other places where to give recommendations and recommending that we do need large databases activities.
Yeah.
That's absolutely. We are the only community, the only scientific community probably without large databases.
Yeah.
And that's a real need.
Can I, yeah, one of the things that we talked about is that, Iris Pascal is an example of good database for seismic data and instrument pools, but seismic data somehow is a little bit more uniform, or somehow that community was ahead of volcanology. Some of that data is volcano data. But, and then there's the community UNAVCO, where some of the GPS data is archived, and that's starting to come on board. But so much volcanological data is tricky to database because it doesn't take a simple form where the sampling rates are continuous through time. Some of it's qualitative characterization. And so that is something that was brought up at the workshop, as well as I think ultimately ended up in the report, which was, not only this kind of simple time series geophysical or geodetic data should be databased, but these other kinds of data. And a big challenge, I think, is to figure out what format that data should even be in.
Well, I think there is room for international commission on database, for technological databases, to define this kind of products and define an international reference.
It's a complex problem, but yes. And I think it goes back to Mattia's question, is part of that is why the big data number crunching isn't quite, we're not there yet. That's not something that's obvious to do. Were there any other questions? I somewhere, I think I have a PDF of this report, but not the final one. I need to find it. So if anyone's interested, you can just send me an email for a digital copy. And then maybe I have a couple of copies at home, which I can put in the library as well. So, and I also can leave this presentation. It has a whole bunch of other slides at the end because I reorganized it, but it does contain the bullet points basically. So. All right.
Thank you very much.
Thank you.
I don't want polemic.
No, I'm with you. Thank you. You have a copy of this, no? You got it IFC. Everyone?
I didn't take it because I arrived too late.
Oh, okay. Yeah, it should have been in your backpack.